next speaker is Duncan Haldane, renowned for his contributions to the topological phases of matter and for the so-called Haldane gap. For this discovery, he was awarded the Nobel Prize in Physics in 2016, alongside David Tolles and Michael Kosterlitz. He is currently a professor at Princeton University, and we are so fortunate to have him here today to give us a talk called Topological Quantum States, Quantum Entanglement, and the Second Quantum Revolution. Please give him a big round of applause. Thank you so much.
Buenas tardes, gracias por la invitación. La presentación será en inglés. Thank you. I'm going to tell you, I hope not too simply, about stuff that people are excited about in modern quantum mechanics and stuff I'm working on in topological quantum states. Okay, so the modern laws of quantum mechanics were established 100 years ago in a short period, and they haven't changed. So they stood the test of time, and all tests of them have confirmed that they're correct so far. But until recently, the result from quantum mechanics that made most impact on the public, that the idea was the Heisenberg uncertainty principle, that you can't measure something at the same measure position and velocity, or measure two things at the same time, or you interfere with things by measuring them. But and also the idea of quantum tunneling, which is sometimes said to be that the idea that you can leave the room by two doors at the same time, or when you come to a fork in the road, take it, as the famous Yogi Berra has said. But in recent times, the ideas viewed as central to quantum mechanics is now the idea of entanglement, I believe. And so starting around 1980, sort of new insights in quantum mechanics started to emerge. And in condensed matter, unexpected topological states of condensed matter started to be discovered. And more recently, these developments in the quantum mechanics of condensed matter have become connected to quantum information theory, which Richard Feynman started thinking about in the late 1950s. He started thinking about what would happen if I made computers smaller and smaller till I got to the atomic scale. And you know, these ideas have come together in recent years, and now the experimental exquisite control of quantum states is a central aim that's being achieved. Earlier work was essentially taking a hammer and smashing a quantum state, or now we're trying to gently probe quantum states and manipulate them into doing things like processing information. And because of these ideas, some people now are saying that we're in the second quantum revolution, 100 years after the first quantum revolution. Certainly when I started my career in physics, no one really talked about entanglement. It was a philosophical idea. Now everyone is talking about entanglement. So there's somehow entanglement has taken over as this central idea in quantum mechanics. And there's a lot of developments happening, and I believe that you know, in the next few years, some of these things are going to come to fruition. There's a whole dream of quantum computing, but there's going to be a whole lot of new quantum sensor technology, which is going to be important too. So let's just go back to some basics. Modern quantum mechanics started in 1926. It goes back. Earlier ideas were the Bohr atom, which was the picture of a little solar system, the electron orbiting around the heavy nucleus in the hydrogen atom. But the modern picture is now the electron is in a cloud around the atom. Now, the original Bohr picture talked about orbitals, the idea of orbits around the atom, and this is going to be replaced by the notion of the orbital, which is the kind of box in which you electron sits. And so the box which contains the electron is still called an atomic orbital, and I'm going to stress that later in the talk. So Heisenberg uncertainty principle turns Bohr's orbit into a fuzzy cloud centered on the nucleus, and we don't know exactly where the electron is, but we know it's in the box. Okay, so from this viewpoint, the orbital is a box which either can be empty or filled. I'm neglecting spin for the moment, so this is like a two-state system, the basic system in quantum mechanics. Two states, spin up, spin down, or empty and filled. And of course, we don't yet image the hydrogen, the smallest orbital of the hydrogen atom, but there's a lot of work now with Rydberg atoms, highly excited Heisenberg atoms, where we can actually image the orbit, and we actually use Rydberg orbits are now greatly used for quantum information ideas. Okay. So the Pauli exclusion principle says that two electrons, which are fermions, can't be in the same state. So what defines that state? In addition to the position of the electron, we also have this internal degree of freedom, the magnetic moment, which is like a little spinning top. And so when we say what is the state of the electron, we're talking both about its spatial position and its spin. And when we put two electrons in the same box or in the same orbital, we can put them in only, according to the Pauli principle, only if their spins are pointing in opposite directions, because we can't put, no two electrons can be in the same state, according to the Pauli principle. So this is the maximally entangled state of the two electrons, is this one where they spin up and spin down. But quantum mechanics says, since the electrons are identical particles, we can't say electron 1 is spin up and electron 2 is spin down. It's a mixture of the two things. They have to be identical, and the Pauli principle tells me in the quantum wave function that if I exchange the pair of electrons because they're fermions, I get a -1 factor, which is basically why you can't put two electrons in the same state. And of course, spin up and spin down could be spin right and spin left. It's equivalent to that. There's no special choice of spin direction in this singlet pair. And this is the maximally entangled state of the two electrons. So of course, this kind of entanglement is everywhere. The chemical bond that binds us all together is basically putting two electrons in between two nuclei, say the hydrogen molecule, and so basically to fit in the bond, to be in the same place, essentially they have to be spin up and spin down. So the chemical bond is a maximally entangled state, and it's everywhere. And in fact, from the point of view of chemistry, perhaps until recently, the pictures I've shown of the little boxes are perhaps the only quantum mechanics that chemists really need to know. At least that's what you learn at school. Okay. So, as I say, the central theme in this new approach to quantum mechanics is this entanglement property. And it actually was recognized by Einstein as a central property of quantum mechanics. And now it's often viewed as a kind of fuel which will drive future quantum information processors. Okay, so where does Einstein come in? Einstein, of course, got his Nobel Prize not for his work on gravity and relativity. He got it for the photoelectric effect, which is one of the two early quantum mechanical things which were identified. But by he got this of course dates from 1905. But by 1935, he'd got round to rejecting the quantum theory, and he pointed out this curious property of entanglement, which he felt just had to be wrong. Now, entanglements Einstein called it spooky action at a distance, or spukhafte Fernwirkung, I believe. Schrödinger came up with a much more neutral term of entanglement, and entanglement is an interesting word because if you look at its roots, in almost every language has adopted a different term for entanglement. In German, it's Verschrankung, English entanglement, intricación in French, entrelazamiento cuántico in Spanish, and something even more complicated in Portuguese I learned last week when I was in Portugal. So entanglement is, Einstein pointed this out. Now, Einstein's famous for Einstein's greatest mistakes, perhaps the cosmological constant, which he thought was his greatest mistake. But Einstein's mistakes have always been extremely fruitful. Both in the cosmological constant is now believed to be possibly the explanation of dark matter, and this spooky action of quantum mechanics is now seen to be a central property of quantum mechanics. So around 1935, Einstein's collaborator Podolsky went public with this. Einstein, Podolsky and Rosen came up with a thought experiment that Einstein felt would demolish quantum mechanics if it could ever be carried out. Podolsky actually went to the newspapers with it, and in 1935, I guess Germany or somewhere, no one had invaded another country that day, so there was so it somehow made the front pages. And in fact, Einstein was furious about physicists washing. He said physicists shouldn't wash their dirty linen in public, and I believe he never talked to Podolsky again. He was very angry with Podolsky for going public on this. But Einstein's idea is, of course, I have this entangled state which I have in the chemical bond, and I pull the chemical bond apart and stretch it without breaking this entanglement property. When they're very far apart, this says the fact it's 50% up, down, and down, up, that if I measure one particle spin to be up, quantum mechanics says you'll always measure the other particle spin to be down, and that superficially sounds like a violation of relativity, that something happens over here and something instantaneously is changed over there. That's actually not true, because you can easily you can take a laser pointer if it's sufficiently fine and make a spot on the moon and make that spot travel across the surface of the moon much faster than the speed of light. But it doesn't mean that anyone can use that for transmitting information from one point to another. And so there's actually no transmittal of information, so there's no violation of relativity in this. Okay, so this has a long history, and the experiment that Einstein, Podolsky, and Rosen proposed was only carried out much later, after the death of the participants. But a recent Nobel Prize finally rewarded the people who put this to the test and showed that no, quantum mechanics behaves exactly in the spooky way that Einstein thought was crazy. So what's about this? So entanglement is shown to exist, and it can happen over large distances, but it's very, very fragile. And that's the big problem in using it. And but now with light, because light has come to us, photons have arrived to us from, soon after the Big Bang, when the universe separated out into neutral atoms. The microwave radiation has come to us unchanged, essentially, over a huge time, so photons can actually travel long distances without becoming entangled with the environment and maintain their properties. So now we have optic fibers can produce entanglement of large distances. Okay, classical information. Let's go moving on to information. Classical information is stored in a bit, which is a switch, which is either on or off, basically the binary system. But quantum information is stored in the properties of a two-level system, or for example, a single spin, which is called a qubit, and instead of just being up or down, it's given by a complex number. But basically, the qubit can be viewed as an object that can point on any direction on the surface of a sphere, but you can only measure its projection onto a given axis. So there's a lot more information in principle stored in a qubit than just the up or down binary numbers, which is why people think we can use this for quantum information processing. So classically stored information is unaffected by reading it or copying it. So there's all this business about breaking copyrights and downloading music from the internet. It doesn't cost anyone anything. You've made a copy. That argues that you haven't stolen anything, but in fact, it's actually difficult to get rid of classical information. You have to do a certain amount of work, a minimum amount of work to erase the classical information. So the qubit stored information is much more richer, but it's much more fragile. In particular, there's two things we can say. The qubits can't be cloned. You cannot copy the quantum. You can't make a multiple copy of the information like you could for some rap song off the internet or something. If you copy it, you wipe out the original when you make the new copy. But actually, there's interesting things we can make we can take information over here and copy it. So by teleportation, by using entanglement, so the information has moved from here to here, even though the original information was destroyed. It's now been teleported, as in Star Trek, I guess. So yeah, these are some of the two central things. The no cloning property, that we can't copy anything without destroying the original, as we see here. We can start from this qubit and take a blank qubit and with no quantum information in it, and we ended up with a blank qubit over here and a copied one. Okay, and similarly for the quantum teleportation, there's this strange thing that we start with. We now make a well-separated entangled pair, which is represented by the dots connecting these two qubits on either end of this in stretching. And we can take the qubit on the left and a known qubit that we want to teleport over here, and we can make a measurement. Whoops. I'm going forward. Whoops. Go back a bit. Yeah. So we make a measurement of this joint system of two qubits here, which has one of four possible outcomes. And then we have to, since nothing gets transmitted instantaneously, the experimentalist over here can pick up the telephone and tell the experimentalist on the other end of the entangled qubit which of the four results he got for the measurement. Using that information, then the right person can use that information to carry out an operation on the right-handed qubit to reconstruct the original state, and we get left with a locally entangled pair with no information content left on the right-hand side. So this is the famous teleportation of the thing. So these are the kind of two strange things. And this particular protocol has led to the idea that entanglement, especially entanglement over large distances as opposed to the common entanglement of the chemical bond, is a resource that will serve as the fuel for quantum information processing. Okay. So how do we produce this long-range entanglement? Well, any two systems placed in contact will become weakly entangled, but we want to actually make these Bell pairs, which are these maximally entangled states. And in chemical bond, the Pauli principle forces the entanglement, but over large distances we don't have that going for us. And to make an entangled Bell pair, we actually have to start with two qubits in known reference states. Their spins both pointing up and both pointing up. The standard method is essentially to bring them into contact by coupling them with what's called a gate. So this causes the singlet and triplet states of these two spins to be separated in energy, and we wait a certain amount of time, and after a precise amount of time, depending on the structure of the gate, if we switch it off, if we remove the gate, we'll have created a perfectly 100% entangled pair. However, that's a delicate operation. We have to turn the gate off at exactly the precise moment to get complete entanglement, and there are various protocols for trying you're never going to do that precisely, and there's various protocols for trying to improve that. But I'll come back to what I call topological quantum states, which is my interest in this subject. They have the possibility in principle at least, to replace this delicate kind of handling and procedure with a robust procedure. Okay. So going back to condensed matter physics around 1980, condensed matter physics had this usual thing that happens in branches of physics where they felt they've solved all the basic problems. It was there a little bit before quantum mechanics emerged. People thought they understood pretty well everything after Maxwell, except a few details about atoms were kind of not quite clear. And suddenly there was a revolution. So in 1980, condensed matter people had worked out the laws of magnetism and phase transitions and things called renormalization group and all kinds of fancy stuff. But two things happened around that time, which actually happened almost in the same place and the same time in Grenoble, France, but in laboratories a couple of doors away from each other. Two examples of what were weird properties were found at the same time, and now we understand these weird properties to be these were topological states of matter, something which hadn't been even dreamt of at the time. So the two things are some more minor thing that I did involving quantum magnetism, and a much more practical thing called the quantum Hall effect, which were discovered by von Klitzing. And now many more examples. These things were not initially recognized as topological, but they've now been seen to. They're not initially recognized to be in any way related, but now it turns out they're part of a much larger scheme, and there's many kinds of topological matter have been found in the last decade or two. So topological matter differs from ordinary matter because it has entanglement properties that can be described by whole numbers. So usually in physics you do very high precision measurements, and you want to measure the fine structure constant or something like this, and you want to measure it to 12 places of decimals because someone has calculated it using Feynman diagrams to 12 places of decimals, etc. And so those are very precise measurements, but these are measurements where you're measuring something to be either 1 or 2 or 0, an integer number. And so that's actually the surprise. So you might say ordinary matter is described by, we might call them boring numbers, although 0 and 1 are not actually boring numbers, but ordinary matter might have a number like 0, but the classification of some topologically non-trivial matter might have some integer. And the states of matter which are described by different whole integers, they cannot change smoothly into each other. I can't go continuously from -2 to 0. If there's a region of this piece of matter where the internal state is characterized by the number -2, and it's embedded in a region. Oops. I'm going forward. Oops. Embedded in a region where 0, there has to be a boundary. And this is a characteristic property of topological matter. There's always an interesting boundary between the topological region and the non-topological region. Okay. And so the fact that the topological properties can't change continuously makes them kind of robust. So small amounts of disorder and dirt don't ruin the topological properties of the material. This is quite in contrast to today's technology based on silicon wafers, where you need a clean room with yellow lights in it, and these kind of spacesuits that the people are wearing and the workers are wearing are not particularly to protect them from the noxious chemicals used in producing the silicon wafers. They're to protect the silicon wafers from little bits of spit or hair or something that might drop off the workers and completely ruin that chip, that whole plate. Oops. I keep doing the wrong thing on this. Okay. So the classical example in mathematics of topology, the original one really, is the classification of closed surfaces or by the genus or number of holes in the surface. So if I have the shape like a sphere, like a soccer ball, and I can distort it into a rugby ball by squeezing it, it's topologically unchanged. But it requires, and I can do that continuously. I just increase the ellipticity of the ball as I squeeze it. But I can't go continuously to a donut shape with a hole in the middle. I have to do a significant amount of work to damage this object sufficiently much that it has a hole in the middle. So holes are described by whole numbers. There's no such thing as 0.3 of a hole. So of course this is the classical thing. Anyone who's sat through a experimentalist giving a talk about their topological matter will realize that they can't stop themselves from showing a little movie lifted off YouTube or somewhere that shows a bagel and a coffee cup changing continuously up into each other again. Oops, did that again. I'm not used to this pointer. Okay. So a mug is the same as a ball. One handle makes it a bagel. Two handles, this is called a loving cup. This is like something they showed at the Nobel press conference that they called a Swedish pretzel, which I think was really a Santa Lucia bun. This is a genuine pretzel. It's got 3 holes. It's equivalent to this thing. I'm not sure what the name of this is, but some people have said it's called a California loving cup. But okay, sorry about that. So topologically trivial states of matter can in principle be assembled by bringing the atoms together and just putting them in contact with each other, but not really entangling them. Oops. So topologically, non-trivial states can't be smoothly connected to just free atoms. But to make a topological state, at some point during the formation, as you bring these atoms together, the electron boxes or the orbitals that were centered on the atoms have to get rearranged in interesting ways to get the chemical bonds. And essentially, the electrons get liberated and then rebound in a new state, and it happens at a particular point in the process of bringing them together. Okay, in heavier atoms, electrons in a group of atomic orbitals can become locked together so that their spins are always parallel. The repulsive Coulomb interaction favors the spins being parallel because you get the maximum benefit of the Pauli principle from keeping them from being close to each other in this multi-spin atom. In the rare earth atom, for example, there's 7 boxes here, right? So the total spin of this partially filled shell depends on how many spins are put together, and nominally we call a single spin a spin a half because it's angular momentum. If you treat it as an angular momentum, it's a half h bar. So there's 2s is the number of this integer number is the number of spins that get lined up. So the total spin of a complete group of atoms of spins in a atom, in atomic shell, like an F shell or a D shell, is either an integer or a half integer. And of course the rare earth, which are topical, very important industrially now, are extreme examples of this. So my contribution to this in 1981, so both my discovery and von Klissing's discovery are kind of accidental discoveries that got made because our research path took us somewhere where we were close to something that no one knew existed, and we were sufficiently prepared to notice there was something strange. Okay, so in particular, the picture of these kind of one-dimensional chains of atoms. This is an antiferromagnet, a spin 1 antiferromagnet, because there's 2 spins pointing up. Was this picture of just bringing the atoms together and stacking them close to each other. You stack them together with a kind of magnetic order, so up spin, up and down were neighbors to each other. But this was a classical picture of magnetism at the time. Now, of course, there's a little bit of quantum entanglement, but it's really insignificant due to the interactions. It turned out that there was a new kind of state where essentially the spin 1 which is really made of two spin halves lined up, kind of resplits into, factors back into its spin half bits and forms a entanglement bond with its neighbor. And the interesting feature there is that since every spin is split up into two, and one half, and half of it was used to the neighbor to right and the other half to the neighbor of left, we see this classical feature of a topological state that there's half of the spin left over on the right-hand side of the system and half on the left-hand side. So this was a system built of spin 1 atoms, or atoms with a spin 1 magnetism, and we ended up with spin half of the atomic spin on either side of the system. And that was, and we see also this fundamental connection here, which we can view as entanglement, because if we cut the thing in half, we will find that the left side and the right-hand side have a fundamental entanglement with each other, which is not present in the original picture. So this result was actually contradicted the prevailing consensus, the way people thought about magnetism at the time. But I came at this from a different angle, a different viewpoint, and it seemed an inescapable consequence of the different way I was looking at this system, and it shocked me because I'd also learnt the conventional idea that the quantum mechanics of magnetism was that 1 over s was like a continuous version of Planck's constant, where 1 over s goes to infinity, 1 over s goes to 0 is something like h bar, and magnetism is a continuous function of 1 over s. But of course, s is 2s has to be an integer, so there's a topology in there that was being completely ignored in the earlier ideas. And actually, this thing shocked the magnetism community, and for a while this idea, this to me obvious conclusion from my work, was kind of viewed as completely wrong and nonsense and was actually unpublishable, in the sense it got rejected by 3 journals in a row, for example. And various senior people came out strongly against it. But anyway, controversy in science is great, and I say sometimes looking at the same landscape from a different viewpoint reveals things that have been missed in the previous way of looking at things. And finally, you know, the controversy stimulated new ideas in building materials, like a chain of nickel atoms in an organic background, and other things like the so-called density matrix renormalization group, which is really entanglement properties, where important tools were derived by people trying to make their mark in deciding if this controversial proposition was true or not. Okay, so controversy is actually always good in science, and of course I'm standing here because it was right. So I'm going to come back to this meme at the end of the talk, but here's the meme of this thing is, you might say people, if there's no injury involved, hands always come in pairs which are close to each other. But if we actually assembly an object which is an organism which is a load of people holding hands, there's a free hand at one end, and a long way away on the other end of the chain there's another free hand that they can wave independently or whatever. Okay. So let's move that on. So the other important thing was von Klissing's result. He found, doing a measurement that of an electrical property of a semiconducting device, that the whole conductivity was an integer multiple of fundamental constants. He was actually so shocked, shocked by that. He did the experiment the right way. It turned out that, I'm not sure this talk shows it, but it depends on you being in a magnetic field and having a constant current flowing through your sample. And then you measure a voltage transverse to the current called the whole voltage. The experiment had been earlier done by people in Japan, who probably kicked themselves very hard after this. They did it by making the current constant and putting this device with a constant current in it in a magnetic field. Sorry, they fixed the magnetic field, put the device in, and turned the current up. you'll never turn the current up to exactly the same value, so you'll always see a slightly different value for this Hall conductance. Von Klising did it the other way around. He put a device with a constant current flowing through it and then switched on the magnetic field. It turns out there's a range of magnetic fields here in which you see this perfect conductivity. So von Klising found that his voltmeter was showing the same number each time he did his experiment to about 4 or 5 significant figures. And he first of all must have thought there's something wrong with my voltmeter. And after realizing that it was not, that it was a reproducible thing, it was totally unheard of at the time to get a number that would be the same each time you did the experiment. Okay, usually every time you do an experiment, something is slightly different, and you never get exactly the same number to huge precision. Okay, and of course this has now become the basis of, coupled with the Josephson effect, it's become the basis of the new system of units, and it's got rid of Napoleonic French imperialism by relegating the piece of platinum in a safe in Paris to the museum. Now everyone can build their Kibble balance. So the topological nature of the quantum Hall effect took quite some time to become clear. I mean, it should have been realized initially. It wasn't. People came up with ideas, well, it must be something to do with the background of the dirt that was somehow important and localization. But it turns out an early thing was pointed out by Bert Halperin that in the magnetic field, the electrons go around in little circles because they're confined to a two-dimensional surface in this semiconductor. So in 3 dimensions, they would spiral around the field lines, like the electrons for the aurora borealis or whatever, they spiral around from the north to the south pole. But here they're located, so they just go around in little circles in the interior of this object. The energy is quantized because of periodic motion, and if this is a clean system, the circle just stays put. Its center doesn't budge. But if they're close to the edge, they go bang, 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 and they skip around the edge. But the crucial thing is, since in the middle they're going around, I've drawn them in a clockwise way, the edge current will be always in the anti-clockwise direction. So this is very strange. We've got a system which has an edge to it, and it has a current like a one-way street going around the edge. And that's actually should have been recognized. Of course, people weren't as topological immediately, but people weren't thinking in terms of topology at the time. And in fact, if I have this system, if I have a finite ratio of bulk volume or bulk area to surface perimeter, then all I need is this to give me the Hall effect, because when I get to the edge, the nice quantized energy of these little periodic orbits gets affected by how close they are to the edge, and their energy goes up at the edge. And we see that if the Fermi energy is anywhere in the edge region, which it is for a certain number of magnetic range of magnetic fields, then we have this bulk gap and quantization. And so this is showing we don't actually need to fine-tune the magnetic field. So you actually don't need dirt for this system. As long as you have a finite edge-to-bulk ratio, then there'll be a finite width plateau, a finite range of magnetic fields where you're pinned at the edge. This is actually also quite interesting. We can see from this picture, turns out this is a fluid. The quantum Hall is a fluid, but it doesn't have any hydrostatic pressure inside it. If you actually squeeze it, whoops. If you actually squeeze it, you actually build up a current at the edge. So a bottle of water like this one, it's glass, so just plastic. Well, if I squeeze it, the pressure will go up and resist my squeezing. But there's actually no pressure inside the quantum Hall fluid. But at the edge, what's happening at the edge currents actually are what opposes the squeezing. So everything in this system happens at the edge. Okay. So the integer Hall effect was soon followed by a bigger puzzle, the fractional Hall effect. In fact, people had just decided they fully understood the integer Hall effect, and the number had to be the number multiplying e squared over h had to always be an integer, when of course, again, something happens in the experimental lab, and Dan Sui went and measured this, went up to higher fields, and he found 1/3 rather than 1. So how did that affect the, how did that work out? Well, it turns out that if you have a fraction p over q, you can actually write it as p times q times e over q. So there's still an integer involved, but the only thing that changed was the electric charge from one electron charge to a fraction of the electron charge. And in fact, the moment Dan Sui saw 1/3 e squared over h, he said he already realized this had to be 3 times e over 3 squared. So he immediately realized this system had to have fractional charged excitations. And this is a fractional Hall effect is a remarkable thing. So only 3 people can get the Nobel Prize. So the guy actually, Art Gossard, who made the device, got left out. These guys did the experiment, and he did the theory which discovered this remarkable wave function, which is completely non-standard from the point of view of all the kind of states of condensed matter previous to this. If m was equal to 1, this would be a Slater determinant, a standard thing that people worked with in studying condensed matter. But m equals 3, it's definitely not a Slater determinant, and it's a remarkable wave function. Okay, so, and again, you can see from this that Art Gossard may be a great experimentalist, but if this was presented as an example of soldering ability, you wouldn't get a job at Intel based on this, right? But you can see how forgiving the fractional stuff, the topological stuff is to all this kind of, all these kind of little bits of soldering going on here. So what's happening in the fractional Hall effect is really kind of remarkable. I'll get through to this. So that there's a kind of, in a Landau level, which is what these were in, there's a kind of basis of orbitals which looks like an onion ring. You can, like an angular momentum basis, you can center it about any point, and actually you can make it any kind of shape. It doesn't have to be circular, it can be elliptical. There's a kind of basis of such things. And the Laughlin wave function, which I briefly showed, has a remarkable feature that if the central orbital of this basis of single particle orbitals is filled, the next 2 are always empty. So actually, looking at this more carefully, we can say that each electron, instead of occupying only 1 orbital, as it does in a standard Slater determinant, it actually occupies 3 orbitals. So it actually, this thing is driven by short-range repulsion between the electrons, and by the electron keeping the next 2 orbitals, which are surrounding the filled one empty, is actually lowering the interaction energy, and we can say that 3 orbitals are either occupied or, I'd like to say, attached to each electron. So if the central orbital is empty, the next 2 are, central orbitals filled, the next 2 are empty. And interestingly, that means if I pull the electron out of the system, so I leave 3 empty orbitals behind, this group of this complex of 3 orbitals is only bound together by the fact there was an electron in the middle which lowered its energy by surrounding itself with a vacancy. So once I remove the electron, the group of 3 empty orbitals will split up and go their own ways to lower the Coulomb energy. And we can see that if I only removed 1 electron, therefore these orbitals actually carry minus 1/3 of an electron. So we can see that that some of the remarkable features of this thing are present in this simple cartoon picture. So a lot more happens in this. There's fractional charge. It turns out these objects with 1/3, if you exchange them, you can only exchange them in a clockwise or anti-clockwise fashion because they're confined to a 2-dimensional surface. And the usual argument that says if I exchange things twice, I get back to where I started from. So I can only have a +1 fermion boson or a -1 fermion under interchange gets modified, and these things can pick up complex phase factors, in this case e to the 2 pi over 3. And so there's a lot of really interesting thing going on. This stuff took a long time. Some of these properties have taken a long time to be experimentally determined. The fractional charge was determined much earlier using shot noise experiments. Like when you hear rain falling onto a tin roof, you can hear the difference between between a small number of large droplets and a large number of small droplets, so you can hear from the shot noise what the charge of the charge carriers are. But it took some more time to show that you had this strange feature of non-fermionic or bosonic statistics when they interchange them. Okay, so I did make another contribution to this, which didn't get mentioned in the Nobel Prize, probably because although I suspect it's actually the real reason I got the Nobel Prize, probably because they wanted to leave this topic open for further prizes, that you can actually get rid of the magnetic field needed in this quantum Hall problem. It turns out that you only need to have broken time reversal symmetry, because if edge currents go around one way, if you make a movie of it and show it backwards, you'll see them going around the other way. So it clearly requires broken time reversal symmetry, but you can achieve that with ferromagnetism inside a sample, and this is something called the Hofstadter butterfly, but you add some term to this and it opens up this whole region here, and this whole region here carries a quantum Hall effect with this is an integer quantum Hall effect with the number 1, E squared over H, but you go completely, if you keep the chemical potential of Fermi level here, you go from 2 bands of this graphene-like model, empty, go all the way through to them both filled and staying in the gap. So you see this remarkable thing: if I stay in this gap, the charge density in the system will vary continuously with the magnetic field. And that's actually a very remarkable property, because how can you have a gap in the system and you vary the magnetic field? The charge density varies. That sounds like a violation of gauge invariance, right? Well, it turns out it doesn't violate gauge invariance, because there have to be these one-way edge states. And when I change the magnetic field, I'm changing the periodic boundary condition for going around the edge, and as I change the flux through the center, I'm pumping states up and down between the bulk. And the remarkable thing is then that the density of electron orbitals inside the bulk is changing as I change the flux. So when you think more closely about that, it tells you that the electron orbitals in a quantum Hall system are free to move. They're detached from the lattice, and their density is not controlled by the density of unit cells anymore. And that turns out to be a key thing. I would just say that more recently, the fractional quantum Hall effect has been seen in these Moiré systems, where you need a flat band for the interactions to dominate the kinetic energy. If the kinetic energy dominates in a partially filled band, then the system will just form a standard Slater determinant state. If you switch off, make the bands flat so the kinetic energy becomes irrelevant compared to interaction energy, then this thing where you group, where an electron wants to occupy more than one orbitals to kind of insulate it from the repulsion from the other electrons, can occur. And there's a lot of work now in these Moiré systems where you now make a system of quantum states on a scale much larger than atomic by having two closely related patterns of things. So okay, so the Laughlin and state and the other early fractional Hall states are abelian states, but even more remarkable than these are the non-abelian states, which people have a dream of using for quantum information processing. And some of these actually, they can hide quantum information in entanglement structures. And some of these things, none of the ones which we've seen, we believe we've seen the one kind of non-abelian, but the kind that there's another, an even further generalization which supports so-called universal quantum computing hasn't yet been discovered, but they're known on paper. So some of these ideas go back to this fellow, Alexei Kitaev, and these guys, Moore and Reed, found there's a non-abelian state at 1/2 of Landau level filling, which is p equals 2 and q equals 4, it turns out. And by braiding these things around, you have interesting stuff happening. But in this kind of state, there's actually hidden degeneracy in the ground state of the system, which grows each time I add an extra of these kind of defects to the system. And what you're doing is manipulating a degenerate ground state, which is kind of like a multi-component qubit. Okay. So in this particular case, I may get to the end. we have these interesting excitations that can't be created locally. You cannot create them individually locally. You can create a double excitation locally and pull them apart into two halves. And I'll tell you that these actually can be viewed as half of an electron box, half of an orbital, it turns out. When these things come together, they can be viewed as a single orbital that can either be empty or filled. When I pull these things apart, they're actually like two half orbitals. The orbital is now split into two distant halves, and the whole thing can either be empty or filled, but the information about the filling is not contained in the orbital itself, but in this region in between. So I can make another state of the thing which looks identical to the outside world, but it was created by pulling these apart, and it has a different pattern. And this one corresponds to the qubit pointing up, and for this particular case it corresponds to a qubit with its spin pointing in the equatorial region. And if I move these things around each other and cause the entanglement patterns to mix by pulling one through the other, I'm manipulating this quantum information that's hidden from the outside world, so long as the things are far enough apart on a certain scale. Okay, so this is a kind of dream of topologically protected quantum information processing, where the information is contained non-locally in these entanglement patterns, and if a cosmic ray goes through the system, it only has an exponentially small chance of destroying the information because it's been spread out. In this case, the information is only danger of being compromised in the initial state where you read it in, where the two things are close to each other, and when you have to bring them back together to read the information out. But in principle, provided they're far enough away on some kind of exponentially falling off scale due to tunneling, then you can carry out as many of these braiding operations as you want on paper. Anyway, that's the story of the thing. This actually is being followed up by Microsoft. Have put a lot of money into a version of this. Unfortunately, we haven't really got any proof of real success in this. Microsoft announced an architecture based on this, but we're still waiting to see how good it is. There's an issue about getting things far enough away from each other because there's an exponential decay length. The topology is not precise in the sense that the corrections to topology are due to tunneling, which falls off exponentially. So long as things are far away from each other on this microscopic scale, the topology is perfect. But of course there is this microscopic length scale, and the question is whether the Microsoft devices are big enough that the separate half orbitals are there. So quickly, this stuff actually goes back to Majorana. Ettore Majorana was a kind of interesting physicist. He's slightly strange. He actually came up with the Majorana fermions, real fermions, taken by splitting the Dirac fermion into real and imaginary parts. But he couldn't be persuaded to write up his paper, so Fermi wrote up his work for him. And then later he disappeared in mysterious circumstances. So Majorana came up with this thing, and it turns out it originally was thought to be a theory of the neutrino. It may or may not be that, but it has a lot of applications in superconductivity, at least formally. And this is actually the picture of this remarkable thing of the two half orbitals. My original work, which splits a spin 1 into two spin halves, is kind of completely not at all as strange as the idea of splitting an electron orbital into two halves, which are separated by a distance. Okay. So these objects are called Majorana zero modes on either end of the half orbitals. And anyway, this is the kind of the picture. To make a qubit, because the fermion number is either even or odd, we actually need 4 of these objects to make an elementary qubit, and both orbitals are one possibility is both orbitals are both empty or they're both filled, so the fermion number is the same in the two, and I can mix these two states. There's a selection rule: I can't mix states with opposite fermion parity. And so I got a qubit which is downspin would be that, upspin would be that, for example. And indeed, we process the information by moving them around, and there's no delicate timing needed in this kind of device. Okay, so this is a beautiful dream, topologically protected quantum computing. It works on paper. Fusion, which we heard about earlier today, works on paper too. So whether it actually comes to fruition, I don't yet know, but I'm pretty confident that anything that all the toy models on can make, people now know how to actually build them. So someday we're going to have, I believe, a working version of this, but maybe there's all kinds of difficulties on the way. Oops. Go back. So quickly, it's a beautiful dream. In the superconducting wire model, which is underlying what the version of this that Microsoft are using, we actually can use Majorana thing to split a simple electron orbital into a real and imaginary part, which is purely a mathematical device when they're not separated from each other. But the device in these superconducting things, you couple them to a superconductor, so they get split up, but they recombine with the neighbors. The green bit and the purple bit recombine on neighboring sites, leaving exactly half an orbital here and half an orbital here, which is the same kind of meme as I showed. So this is only one of the ways. The more conventional qubits are certainly doing much better. There's a huge amount of progress in making the lifetime of the information in standard qubits bigger and bigger. But in principle, they're always subject to exponential, the law of exponential. You make things bigger, there's always going to be a time scale that kills you. But in any case, there's going to be a lot of interesting things going on here. So finally, qubits are not just for quantum computation. Whether or not people are starting to think we're going to get, really working quantum computers quite soon, but we'll see. But there's going to be a whole lot of new technologies. Qubits, we can use the qubit because it's such a sensitive coupling to the environment. That also gives us a way to measure the environment very sensitively. So there's a whole new range of quantum sensing devices based on things like nitrogen vacancies in diamond, which could be used to get incredibly accurate measurements of the magnetic field, maybe they'll hear what you're thinking about by reconstructing all the currents in your brain and handing it to AI to decode your thoughts. Also dropping atoms in, watching the atoms fall gives you incredibly sensitive measurements of the gravitational field, and you can measure, discover what's under the ground and under all sorts of things. I believe they're talking about using the NV center to precision mapping of the Earth's magnetic field, so you have a fingerprint from each point on the Earth's surface. So if the GPS gets switched off by some malevolent power, coupled with AI, you could still find out exactly where you are by comparing the magnetic image of the ground to maps. So we actually, all this stuff needed three communities to collaborate with each other. I'm a toy model builder. I found it I learned from my advisor Phil Anderson that to reduce things to the simplest possible thing, to get rid of all the details of a problem, and if the physics is still there, those details were not essential, and those lead to things where you can actually solve problems in a way to actually see something strange happening. We actually, of course, all this stuff turned out to need deep mathematical understandings of what explained the stuff one saw there, and of course material science to actually turn these things from dreams into reality is the crucial thing. So finally, I got a motivational message. Both the two things I described were luck. Von Klitzing's luck was to carry out his experiment in a particular way. He was in no way had any idea that was a crucial aspect of the experiment. I started working on one-dimensional materials and bosonization or whatever, but I realized I could apply something else I was doing to this magnetic problem, initially the spin half problem, which sort of had an exact solution behind it that looked like it agreed with the general idea of magnetism. And it turned out there was the exact solution of the spin half version of this chain has nothing, although it superficially resembled what spin wave theory, which is what people in magnetism were using, it completely fooled them and into thinking 1 over s was a continuous variable. And so I was quite as shocked as von Klitzing was to find something completely contradicting the standard ideas. And so anyone who's working on basic research, if they've got a little bit of time, if they allowed 10 or 15% of their time not to completely march forward along the program direction, but if something unusual shows up on either side of their research path, to actually check it out. Most of the time, that'll be slightly interesting that you find, and then you can move on. But very occasionally, it's a bit like you're walking on a beach, like if there was a pirate, if it was known a pirate had buried his treasure on a particular beach, there'd be 100 people digging holes all over that beach, because there's lots and lots of smart and motivated people who are going to go. And if anyone has an idea there's something to be found, they'll be out there looking for it. So you don't have a chance. But if there's something that no one knows is there, you're walking along this beach, a deserted beach, and you're kicking the dust or the sand. If you're not looking at your feet, you might not notice you've unearthed a little piece of treasure as you walk on by. But if you notice something of your surroundings and something is odd, you may have the luck to unearth something that changes the way we think about a given field, and that's why I think anyone working in basic science who has a little bit of time has some chance of finding these discoveries, because it's not just being a super brilliant genius. You need luck to actually push you. Luck in your research path, which you don't know, which is controlled by random forces, that brings you close to something that is so amazing that it changes things. Of course, you do need the preparation to be able to recognize that something you saw is actually interesting and dig it up and find out its thing. So there you go. And then, of course, you need preparation, and you probably need commitment, because if anything is really going to change the way people think, there will be a lot of fight back against it. Thank you.
Okay, thank you, Duncan. We'll start with the question.
Thank you for your speech. I was really interested in the part of Majorana fermions here.
Mm-hmm.
Here.
Oh, there.
It's rather a trivial question, but I was interested in the part because I'm doing my bachelor thesis about that, and I was interested in the part of what makes Majorana zero modes topologically protected.
Okay, so the Majorana zero mode is not a fermion. It's half of a fermion.
Right.
So the Majorana as a particle is just a regular particle, right? But in a superconductor, you can get these things. So the orbital, instead of being a kind of mobile particle with a kinetic energy, it's in a local orbital, and this local orbital can get split. So it can either be empty or filled. You get it, for example, originally in a superconductor, I guess you need an even parity, an odd parity superconductor, which is basically not spin up and spin down, but just one kind of spin. Okay. So you have if spin up and spin down are separated by spin-orbit coupling, so the superconductor V is essentially one kind of spin, which may be varying from place as energy, but then a pair of particles has to be in an antisymmetric state under interchange. It's called an odd parity superconductor. If you take a vortex in odd parity superconductor, it has an orbit. The center of the vortex has an orbital, which can either be empty or filled. Okay. But it turns out you can split that vortex into two half vortices, each of which contain a Majorana zero mode. So that's the original thing is like a local box that can either, and you can look at it. It looks different if it's occupied or empty. But once you pull this thing apart, the information about whether the box was empty or filled is somewhere in the middle between the two. When you look at the split pieces, you can't tell by looking at them whether the box was initially filled or initially empty. If you look very closely, you see that the filled or empty state differ by very tiny little interference fringes, which have the phase of which tells you which. But as I split them apart, these interference effects die off exponentially, and you can't see them. So provided they're far apart on an exponential scale, which is due to how far outside the little half orbital the charge is confined, then you can't tell the difference. And so the Majorana particle, the Majorana zero mode is not a fermion. It's half a fermion, and it has interesting exchange. It's a non-abelian fractional statistics particle.
And according to your criteria, how far are we from topological protection in those terms?
Well, I'm not involved in the kind of material stuff. So, I mean, this has gone through, like, initially people were very bullish about this. 1917 was supposed to be the year of braiding, right? But, you know, and it was announced in Holland and stuff that they'd found, in Delft, claimed they found the Majorana zero modes experimentally. But unfortunately, 2017 kind of came and went, right? And it turned out that wasn't Majorana zero modes that they'd found. It was something called Andreev bound states. So Microsoft made these announcements. There's a large amount. They have some very glossy YouTube movie about Majorana 1, the architecture and the chip. They have a picture of a thing with Majorana 1 written on it. But you know, they kept quiet about it for a long time. And so my understanding is that the issue is partly to do with how well localized. So this thing has a structure. The 4 qubits, the 4 Majorana modes are structured like the endpoints of an H, right? And they decay. There's a decay length from the end inwards towards the bridge of the H. And you do one kind of measurement at the bridge, and another one you do by tunneling across between the 2 points above and below the H. So it's a question of the exponential localization length. The topology, when the quantum Hall showed up, people started asking, you know, what are the corrections to von Klitzing thing? Are they relativistic corrections? In fact, if you use SI units, which are the ones we're all trained to use, except my colleagues in the US still have a hard time abandoning Gaussian units, E squared, the conductivity constant is E squared over H. There's no C in it, right? So it's actually nothing to do with relativity. It's to do with quantization, the quantum of the charge and the quantum of Planck's constant. But people thought, is there some kind of relativistic correction? And they looked for it and no. And it turns out the only corrections to the accuracy of the plateau are how far the edges of this Hall bar are far away from each other, and how clean they are, because there's an exponential, the edge states leak into the bulk exponentially. So provided the distances between the edges is large enough that the exponential tunneling, small tunneling between the edges can be neglected, then the plateau topology becomes exact. So again, that's the issue in this Majorana 1, as far as I can see, the length of the H, how far the decay of, how localized the Majorana zero mode. There's a toy model called the Kitaev chain where the Majorana mode is 100% localized at the edge of the thing. But that requires, that toy model requires very, very high precision tuning, and any details will, any further material details will do that. So a real system will always decay exponentially. So part of the thing is making these things decay. And then there's another issue of stray fermions called fermion poisoning happening. I mean, but people are still looking for this. The goal of people, the dream of people, when they, especially with these new flat band materials, is to try and find the system which has so-called Fibonacci anyons, which would give you this universal quantum computing. The Majoranas themselves, they have because of the fermion number issue, they're not totally, there's one gate you can't, I guess it's the Hadamard gate or something, there's one gate you can't construct in a topological way from the set of gates which are needed for, quote, what's it called, universal quantum computing. But on paper this stuff works beautiful. And in fact, some of the qubits that people have been making, the virtual qubits, people like Quantinuum have made, some of this stuff has actually been simulated and shown to work under simulated with actual qubits. But of course, we don't want to use a large number of actual qubits to simulate this stuff. We want a physical qubit of this to be able to build actual things. But the principles sort of work on paper, and they've been somewhat shown by simulations with qubits. So in that sense, there's no doubt that the principles are there, but there's no doubt that the fusion works in principle, provided you can overcome the technical barriers. So until it's actually done, who knows? But I think it's going to get done personally. But
Thank you.
don't invest your pension fund based on